up your smartphone. Go ahead, just look at it for a second. It's a smooth, black rectangle of glass and metal. It feels solid, maybe a little cold. It's the single most important object in modern life. Our map, our memory, our connection to the world. But here is the wild part. Inside this device, which fits in your pocket, is more computing power than NASA used to send Apollo 11 to the moon. Actually, it's about 100,000 times more powerful. We usually talk about apps, cameras, or battery life. But today, we are going deeper. We are going to look at the atoms. We are going to explore the hidden engineering of your smartphone. How do you fit billions of switches onto a chip the size of a fingernail? Why is the glass so tough, yet so clear? And why is there a pinch of gold, a dash of yttrium, and a sprinkle of indium in every single phone? By the end of the next 20 minutes, you will never look at your phone the same way again. We are diving into the world of extreme materials science and impossible miniaturization. Welcome to the hidden world inside your pocket.
Let's start with the first thing you touch, the screen. This isn't just normal window glass. If you use standard glass, your phone would shatter the first time you put it down too hard. This is aluminosilicate glass, most famously known as Gorilla Glass. How do engineers make glass tough? They use a chemical bath. Imagine soaking a piece of glass in a hot bath of molten potassium salt at 400 degrees Celsius, 750 degrees Fahrenheit. At the atomic level, the glass has sodium ions. But in this bath, those small sodium ions leave the glass, and large potassium ions from the bath jam themselves into the empty spaces. It's like trying to fit a tennis ball into a hole meant for a golf ball. This creates a layer of high compressive stress on the surface. That stress makes the glass incredibly resistant to cracks. But the glass isn't just a shield, it's an interface. How does it know your finger is there? Beneath that glass is a transparent conductive layer made of a material called indium tin oxide, ITO. This is materials science magic. Indium is rare and conductive. Tin stabilizes it. Oxygen makes it transparent. Most metals conduct electricity but block light. Think of aluminum foil. Glass transmits light but blocks electricity. ITO does both. It's a transparent wire. When you touch the screen, your body, which is basically a bag of salty water, conducts electricity. You steal a tiny amount of charge from that ITO grid. The phone's processor detects that voltage drop at specific coordinates and says, aha, the user just tapped the Instagram icon. All of this happens through a material, indium, that is a byproduct of zinc mining and is running dangerously low in global supply.
Now let's go deeper. Past the screen, past the battery, to the motherboard. Here sits the brain, the system on a chip, SoC. This chip is likely smaller than a postage stamp, yet inside an iPhone 15 Pro's A17 Pro chip, for example, there are 19 billion transistors. Let me repeat that, 19 billion. If a transistor were the size of a person, that chip would be larger than the entire Earth. But engineers have shrunk them to about 3 nanometers. That is the width of about 12 silicon atoms. We are approaching the physical limit where quantum mechanics starts to mess things up because electrons might just tunnel through walls. How do you build something that small? You don't build it, you print it using light. This process is called photolithography. Engineers use extreme ultraviolet, EUV light. This light is so difficult to generate that the machine used to make it costs over $150 million. It involves firing a laser at a droplet of molten tin 50,000 times a second to create plasma. They shine this light through a blueprint onto a silicon wafer coated in light-sensitive chemicals. It washes away the exposed parts, etching microscopic canyons and towers into the silicon. They repeat this process dozens of times, layer by layer, building a 3D skyscraper of circuitry. Pure silicon acts like an insulator. It stops electricity. To make it a switch, a transistor, we have to dope it. We shoot foreign atoms, like phosphorus or boron, into the silicon crystal lattice. Phosphorus adds an extra electron, N-type. Boron creates a hole or a missing electron, P-type. By sandwiching these doped layers together, we create a gate that can stop or allow the flow of electrons billions of times per second. That on-off flow is the ones and zeros of your photos, texts, and games. Let's look at the camera. How does a flat phone take photos that rival bulky DSLRs? It's materials science again. The sensor is a silicon wafer that turns photons, light, into electrons, data. But the real hero is the lens stack. Your phone doesn't have one lens. It has 5, 6, or even 7 plastic lens elements stacked in a space the size of a pea. These aren't simple glass curves. They are aspheric plastic lenses, molded with submicron precision. High refractive index polymers allow light to bend sharply without distorting. Now turn up the volume. Your speaker and the Taptic engine rely on super strong magnets. If we use normal fridge magnets, the speaker would be the size of a golf ball to get decent sound. Instead, we use neodymium magnets. An alloy of neodymium, iron, and boron creates the strongest permanent magnets known. This allows tiny speakers to push air effectively and tiny motors to vibrate the whole phone instantly. The microphone is perhaps the wildest piece of miniaturization. It's a MEMS device, micro-electromechanical system. Imagine a drum. Now imagine that drum is etched out of silicon and is smaller than a grain of sand. When you speak, sound waves hit a diaphragm that is only a few hundred nanometers thick. It moves, changing the capacitance between it and a backplate. That tiny physical movement is converted into electrical signals. It is a physical machine, with moving parts carved into a microchip. All of this tech needs power. Enter the lithium-ion battery. Think of the battery as a rocking chair. The cathode, positive side, usually made of lithium cobalt oxide, LiCoO2. The anode, negative side, made of graphite, carbon. When you charge your phone, you are using electrical energy to force lithium ions out of the cobalt cage and push them over to the graphite sheets. They sit there, trapped, vibrating with potential energy. When you unplug and use the phone, those ions rush back to the cobalt side, releasing energy on the way. Materials scientists are obsessed with the cathode. Why? Because cobalt is heavy, expensive, and ethically problematic, mostly mined in the DRC. Engineers are constantly tweaking this recipe. They are adding nickel to store more energy and manganese to make it safer. NMC batteries. They are trying to replace the liquid electrolyte, which is flammable, with solid ceramics, solid-state batteries. The goal? A battery that lasts a week. We aren't there yet, but materials science is the only way we will get there. We've covered glass, silicon, magnets, and batteries, but that's just the surface. A typical smartphone contains roughly 75 stable elements from the periodic table. That is more than 2/3 of all the elements that exist in the universe. Tantalum in the capacitors helps manage power flow. Gold is used in connectors because it doesn't corrode. Yttrium and europium are used in the screen to create vivid red and green colors. Your phone is a geological miracle. It requires mining rock from Africa, sand from America, and rare earths from China, all refined to 99.999% purity. This engineering marvel comes with a responsibility. These materials are finite. The hidden engineering of the future isn't just about making things faster or smaller, it's about circularity. How do we extract that gold and cobalt back out of old phones? How do we design alloys that are easier to recycle? That is the next great frontier in materials science. Urban mining. So, the next time you pick up your phone to scroll, verify a transaction, or take a selfie, remember, you aren't just holding a gadget. You are holding the culmination of human engineering. You are holding the Stone Age, the Bronze Age, and the Silicon Age, all melted down and forged into a black mirror. Thanks for listening. Keep exploring the hidden world around you.